In the silent darkness beyond Mars, something is moving the wrong way. An interstellar visitor, 3I Atlas, has slipped from its predicted course by over 1 million kilometres. NASA's models said it should drift. Instead, it moved. Subtly, intentionally, almost as if it knew where it wanted to go. Its glow, geometric. Its spectrum, electric. Its story, just beginning. Astronomers call it a trajectory anomaly. Others whisper about controlled plasma and alien propulsion. But what if this isn't just a glitch in our math? What if we're witnessing a manoeuvre? Stay until the end as we trace the evidence, the silence, and the possibility that something, or someone, is steering 3I Atlas. If these mysteries have your pulse racing like mine, don't just sit back. Hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1, Breaking News Moment. Something is wrong with the sky. Not wrong in the way you'd notice looking up tonight. Wrong in the way that makes astronomers refresh their data over and over, checking their math, recalculating, hoping the numbers will make sense. They don't. An object designated 3I Atlas, the third confirmed interstellar visitor to our solar system, appears to be roughly 1 million kilometres ahead of where it should be. That's not a typo. 1 million kilometres. To put that in perspective, that's more than twice the distance between Earth and the Moon. Objects don't just drift that far from their predicted positions, not unless something is pushing them. The discovery came quietly, as these things often do. Independent observers comparing their telescope measurements to the official ephemeris data from JPL, NASA's Jet Propulsion Laboratory, noticed something odd. The object wasn't where the computer model said it would be. At first, it was a few arc minutes. An arc minute is 1/60th of a degree, tiny in cosmic terms. Measurement error, probably. Bad seeing conditions. A miscalibration somewhere in the imaging chain. But the offset kept growing. Week by week, observation by observation, 3I Atlas drifted further from its predicted path. What started as a curiosity became an anomaly. What started as an anomaly is now something we don't have a good word for. You can visualize this by overlaying 2 tracks on the same chart. One track shows where JPL's orbital model predicts 3I Atlas should be at any given time. This model incorporates everything we know about celestial mechanics. Gravity from the Sun, from Jupiter, from every massive body in the solar system. Solar radiation pressure pushing on the object like wind on a sail. Even subtle effects like outgassing, when volatile ices on a comet's surface sublimate and create tiny jets that can nudge the object's trajectory. The other track shows where amateur and independent astronomers are actually finding 3I Atlas in their images. These 2 tracks should overlap, within the bounds of measurement uncertainty. They don't. The gap between prediction and observation is widening. Several observers have gone on record claiming they're seeing signs of acceleration, not just a static offset, as if 3I Atlas started its journey from a slightly different position than we thought. Acceleration means the velocity itself is changing. Something is speeding it up or slowing it down or changing its direction in ways that gravity alone cannot explain. The central question bleeding through every forum post and preprint article is this. Are we watching deliberate manoeuvring, or are we being fooled by an observational artifact we haven't identified yet? Then there's the glow. Comets glow. That's normal. Solar radiation ionizes gases in the coma, the fuzzy atmosphere surrounding the nucleus, creating a characteristic tail that points away from the Sun. What observers are reporting around 3I Atlas is different. They describe geometric patterns in the ionized gas, zones of brightness that appear structured rather than diffuse. One report mentions regions of plasma that seem almost organized, as if shaped by magnetic fields or directed flows rather than the chaotic turbulence you'd expect from solar-wind interactions. The phrase controlled plasma has started appearing in discussions, and that phrase carries implications that make professional astronomers very uncomfortable. Timing makes this situation more urgent. 3I Atlas is approaching perihelion, the point in its orbit where it comes closest to the Sun. That event is scheduled for late October 2025. Shortly after perihelion, from Earth's perspective, 3I Atlas will pass into solar conjunction. This means it will appear to move behind the Sun as seen from our planet. For several weeks, possibly months depending on the geometry, we won't be able to observe it at all. The Sun's glare will drown out any signal. If something happens during that blind window, if the object fires thrusters or executes a course correction or does anything unexpected, we won't see it happen. We'll only see the aftermath when it emerges on the other side. This is not a conspiracy theory. This is not speculation built on blurry photographs from someone's backyard telescope. This is data. Astrometric data from multiple independent sources showing a persistent, growing offset from predicted positions. The question is what that data means. Science is supposed to peel back layers of mystery until we reach bedrock understanding. Right now, we're peeling back layers and finding more questions underneath. Is this a flaw in our orbital models? A systematic error in how we're measuring positions? An extreme case of cometary outgassing that our standard models don't capture? Or is it something else entirely? The phrase, something else, is doing a lot of work in that sentence. Something else could mean natural phenomena we don't fully understand yet. Or it could mean we're watching an object under intelligent control. If the latter is true, this would be the first confirmed detection of extraterrestrial technology. Not a radio signal, not a strange megastructure blocking starlight. Motion, trajectory alteration. A visitor from another star system that is steering itself through our solar system with intention and purpose. By the end of this investigation, you'll have enough information to decide what you believe, whether this is the moment humanity detected its first sign of cosmic engineering, or the moment we learned just how wrong our measurements can be when we push them to their limits. Either outcome teaches us something fundamental. Either outcome changes how we look at the night sky. Later, we'll compare this situation to past interstellar objects like Oumuamua and Borisov. We'll explore exotic propulsion hypotheses that sound like science fiction, but are grounded in real physics. We'll examine how hard it actually is to measure the position of a faint, fast-moving object millions of kilometers away, and whether the claimed anomaly falls within or outside any reasonable margin of error. This might be the first sign of intelligence in the universe beyond Earth, or it might be the wildest measurement error anyone has ever convinced themselves was real. The data exists. The observations exist. What they mean is still an open question. Before we go further, before we dive into orbital mechanics and plasma physics and the philosophy of extraordinary claims, you need to understand one thing. We may not get a second chance at this. If 3I Atlas is maneuvering, and if it disappears behind the Sun and emerges on a completely different trajectory, we'll know. But by then it will be too late to watch it happen. The action will be over. We'll only be left studying the aftermath. Part 2, Trajectory Anomaly. Deep Dive. NASA's Jet Propulsion Laboratory maintains a system called Horizons. Think of it as the most sophisticated orbital calculator ever built. You input an object, a date, an observer location, and Horizons tells you exactly where to point your telescope. The system incorporates gravitational effects from every significant body in the solar system. The Sun, obviously, Jupiter's massive pull, the subtle perturbations from Saturn, Uranus, Neptune, even the minor contributions from Mars and Venus when they're in the right configuration. Solar radiation pressure gets included too. Photons from the Sun carry momentum, and when they bounce off or get absorbed by an object's surface, they impart a tiny push. For small, lightweight objects, this push adds up over time. Horizons also includes non-gravitational forces. These are effects that don't come from gravity or radiation pressure. The most common example is outgassing from comets. When a comet approaches the Sun, ice on its surface heats up and sublimates, turning directly from solid to gas. This gas jets outward. And if the jets are asymmetric, they create thrust. Imagine a spinning lawn sprinkler. The water shooting out creates a force that makes the sprinkler rotate. Cometary jets work the same way. The object spins, jets fire, and the net result is a small but measurable acceleration. Orbit fitting software models this with coefficients called A1 and A2. These numbers quantify how much the object is accelerating radially away from the Sun and perpendicular to that direction. For 3I Atlas, JPL published orbital elements shortly after its discovery in July 2025. The object was spotted on an inbound trajectory, coming from interstellar space, headed toward perihelion. The orbital solution included preliminary A1 and A2 terms based on early observations. Standard stuff. Every active comet gets fitted with these coefficients. The published ephemeris, the table of predicted positions over time, should have been reliable within certain margins. Those margins depend on how many observations have been collected, how well distributed they are in time, and how much the object's brightness and activity level might be changing. For a newly discovered interstellar object with only a few weeks of data, you'd expect uncertainties on the order of tens of thousands of kilometres, maybe 100,000 kilometres if you're extrapolating far into the future. The reported offset is 1 million kilometres. That's an order of magnitude larger than any reasonable uncertainty margin. It's not a subtle deviation buried in the noise. It's a massive, glaring difference between where the model says the object should be and where observers are actually finding it. If you convert 1 million kilometres into angular terms at the distance 3i Atlas is from Earth, you get roughly 15 arc minutes. That's a quarter of a degree, half the width of the full moon as seen from Earth. You don't miss something by that much unless either your model is catastrophically wrong or the object isn't following the rules. The offset isn't static either. Early reports suggested a discrepancy that grew over time, not a sudden jump, as if someone discovered 3i Atlas had been misidentified and its orbit recalculated. A drift. Week by week, the difference between predicted and observed positions increased. That pattern is consistent with acceleration. If the object were experiencing a constant unmodelled thrust, you'd expect exactly this behaviour. The longer the thrust operates, the more velocity it accumulates, and the further it deviates from the original predicted path. Who reported this? The primary source appears to be an article published on Medium by an independent researcher who had been tracking 3i Atlas using images from multiple ground-based observatories. This wasn't someone with a backyard telescope making wild claims. The analysis cross-referenced observations from professional survey programs, publicly available astrometry databases, and comparison to the JPL Horizons ephemeris. The researcher showed their work. They included timestamps, observatory codes, measured coordinates, and residuals. Residuals are the difference between where you measured an object and where you expected it to be. When residuals start trending in one direction over time instead of scattering randomly around zero, that's a red flag. Has JPL responded? Not publicly, as of this recording. No updated orbital solutions have been released acknowledging a massive non-gravitational acceleration. No astronomer's telegram has been issued discussing the anomaly. The professional astronomy community has been eerily quiet. That silence could mean several things. Maybe they're taking time to verify the claims before making any public statement. Maybe they've identified an error in the independent analysis but haven't published a rebuttal yet. Or maybe, and this is the possibility that keeps people up at night, they're seeing the same thing but don't know how to explain it yet. Let's explore alternative explanations that JPL's models already account for. Solar radiation pressure affects 3i Atlas just like any object, but the magnitude of that pressure is predictable based on the object's size, reflectivity, and distance from the Sun. If 3i Atlas were significantly smaller or more reflective than estimated, radiation pressure could create a larger than expected acceleration. However, to produce a 1 million kilometre offset, you'd need the object to be almost gossamer thin, or have a reflectivity approaching that of a perfect mirror. Observations don't support either scenario. The object appears faint but solid, with no signs of extended structure like a dust cloud or debris field that might increase its effective surface area. Outgassing is the next suspect. Comets routinely exhibit non-gravitational accelerations from jets. The famous case of comet Encke involved precisely this phenomenon. Encke's orbit was observed to change slightly over successive apparitions because jets on its sunlit side created thrust. For a typical comet, the accelerations from outgassing range from billionths to millionths of a meter per second squared. That sounds tiny, but integrated over months, it adds up. To shift an orbit by 1 million kilometres, in the time 3i Atlas has been under observation, you'd need accelerations at the high end of that range, sustained continuously. Is 3i Atlas doing that? If so, we should see dramatic brightening as the coma expands and more material gets ejected. We should see pronounced tails in images. Reports describe the object as dimmer than expected for its size, not brighter. The morphology doesn't match a violently outgassing comet. Mass loss asymmetry is another possibility. If 3i Atlas is rotating and jets fire preferentially from one hemisphere, the thrust vector changes as the object spins, creating a complex pattern of acceleration. This is modelled in orbit-fitting software, but it requires knowing the rotation period, the location of active regions, and the strength of the jets. Without detailed observations, those parameters are poorly constrained. Maybe the models are using incorrect assumptions. Maybe the real outgassing pattern is so bizarre that standard comet models don't capture it. That would make 3i Atlas an extreme outlier, but not necessarily artificial. One case study worth mentioning is asteroid Bennu. When NASA's OSIRIS-REx spacecraft studied Bennu up close, they discovered the asteroid was ejecting particles from its surface. These particle ejection events created tiny accelerations that affected Bennu's orbit in measurable ways. Bennu isn't a comet, it's a carbonaceous asteroid. The fact that it was ejecting particles at all surprised scientists. If a rocky asteroid can do that, maybe 3i Atlas is doing something similar but more extreme, or maybe we're grasping at straws trying to fit square pegs into round holes because the alternative hypothesis is too uncomfortable to entertain seriously. The pivotal data point is the offset itself. If it's real, if multiple independent observers are measuring the same systematic deviation from the predicted path, then everything else follows. The question of controlled plasma glows, the speculation about propulsion, the philosophical implications, all of it hinges on whether that 1 million kilometre offset is genuine or an artifact. If it's artifact, the mystery evaporates. If it's genuine, we're standing at the edge of something unprecedented. Part 3. Spectral, morphological and plasma glow claims. Brightness is one of the first things astronomers measure when they spot a new object. How much light is it reflecting or emitting? Combine that with distance and you can estimate size or albedo. Albedo is reflectivity. A dark object absorbs most of the light hitting it. A bright object reflects it back. For 3i Atlas, the brightness measurements are puzzling. The object appears dimmer than you'd expect if it were a typical icy comet nucleus of a certain size. Either it's smaller than estimated, or it's darker, or something else is going on with how light interacts with its surface or surrounding material. Then there's the morphology. Morphology means shape and structure. When astronomers image a comet, they expect to see a diffuse coma surrounding a brighter central condensation where the nucleus is. As the comet gets closer to the Sun, the coma expands. Gas and dust stream away, forming tails. The gas tail, or ion tail, points directly away from the Sun because charged particles in the solar wind push it. The dust tail curves along the comet's orbit because dust particles have inertia and don't get blown away as easily. These features are well understood. Every comet textbook shows diagrams of comas and tails and explains the physics. What observers are claiming to see around 3i Atlas doesn't fit that template. Reports describe geometric patterns in the glow, zones of ionized gas that appear structured rather than random. Imagine if instead of a fuzzy, irregular coma, you saw distinct regions of brightness, arranged in a way that suggests organization. One description mentioned areas that looked almost segmented, as if the ionization were happening in specific locations rather than uniformly across the entire coma. The term controlled plasma started circulating in online discussions. Controlled implies intention. It implies that the plasma distribution is being shaped by something other than natural processes. In a normal cometary coma, ionization happens when ultraviolet light from the Sun strips electrons from gas molecules. The resulting ions glow at specific wavelengths depending on the molecules involved. Water gets ionized, carbon dioxide, carbon monoxide, various other volatiles. The glow is diffuse because the gas is expanding outward in all directions from the nucleus, and the solar wind sweeps it into a tail. You get irregular structures sometimes, features called streamers or knots, caused by variations in the solar wind or magnetic field interactions. But these structures are chaotic. They change rapidly. They don't maintain geometric shapes. If 3i Atlas is showing structured plasma zones that persist over time, that's strange. One explanation is that magnetic fields are sculpting the plasma. Comets don't have strong intrinsic magnetic fields like planets do, but the solar wind carries a magnetic field with it. When that field interacts with the ionized coma, it can create organized structures. Magnetic field lines get draped around the coma, and charged particles follow those lines, creating patterns. This is standard plasma physics. However, the patterns you get are still generally chaotic and transient. Getting long-lasting geometric shapes would require a stable, strong magnetic environment that doesn't typically exist around small cometary bodies. Another possibility is that the structures are artifacts of image processing. When you stack multiple telescope images to improve signal-to-noise, misalignments or errors in the stacking algorithm can create spurious features. Maybe what looks like organized plasma zones are actually just overlapping diffraction spikes or bad pixels that got amplified during processing. Without access to the raw images and processing pipeline, it's hard to evaluate this hypothesis. If multiple independent observers using different equipment and different processing methods are all seeing similar structures, that would argue against pure artifact. If it's only appearing in one person's images, artifact becomes much more likely. Professional observatories have the tools to settle this question definitively. The Hubble Space Telescope can image 3I Atlas at high resolution without atmospheric distortion. The James Webb Space Telescope can take infrared spectra that reveal exactly what molecules are present and in what quantities. Ground-based telescopes equipped with spectrographs can measure emission lines and compare observed intensities to models. As of now, no high-profile observations from those facilities have been published regarding 3I Atlas. That might mean the object hasn't been prioritized for follow-up yet. Or it might mean observations have been taken, but results haven't been released. Spectroscopy would be particularly revealing. If you can measure the spectrum of the coma, you see discrete bright lines corresponding to specific atomic and molecular transitions. Typical comets show strong lines from water, carbon monoxide, carbon dioxide, cyanogen, maybe some sulfur compounds. The relative intensities of these lines tell you about the composition and how much of each volatile is sublimating. If 3I Atlas shows unusual lines, elements or molecules that don't belong, that would be extraordinary. Metals in unusual states, exotic isotopes, emission from high-energy processes that shouldn't be happening at the temperatures and densities in a cometary coma. So far, no published spectrum exists showing anything like that. Absence of evidence isn't evidence of absence, but it does mean we're operating in a data vacuum. Brightness variations over time matter too. As a comet approaches the Sun, its activity should increase. More heating means more sublimation means more gas, and dust means brighter coma. The relationship isn't perfectly linear because it depends on what ices are sublimating and how fast the nucleus is rotating, and whether you're exposing fresh material or inert dust. But there are models. If 3I Atlas is dimming when it should be brightening, or brightening when it should be fading, that's another anomaly stacked on top of the trajectory offset. Some reports suggest exactly that. Photometric measurements showing variability that doesn't match standard cometary activity curves. The speculative question hovering over all of this is whether the glow zones could correspond to exhaust from propulsion systems. If the object has plasma thrusters embedded in its surface, firing to adjust trajectory, those thrusters would create localized ionization. You'd see bright spots or jets at the thruster locations. The pattern would depend on how many thrusters there are, where they're placed, and which ones are firing at any given time. This is science fiction territory, but it's not physically impossible. Humanity has built ion engines. We've flown them in space. The Dawn spacecraft used ion propulsion to visit Vesta and Ceres. The thrust is minuscule, fractions of a newton, but continuous operation over years can produce significant velocity changes. Scale that technology up, or imagine a civilization that developed it thousands of years before we did, and you could build something capable of interstellar travel that adjusts its course using plasma jets. Occam's razor tells us the simplest explanation is usually correct. A natural comet behaving in an extreme but ultimately understandable way is simpler than an artificial spacecraft. But Occam's razor isn't a law of physics, it's a heuristic. If the data genuinely can't be explained by natural processes, if every conventional explanation fails under scrutiny, then you have to consider unconventional ones. We're not there yet. We don't have enough data. What we have are suggestive hints, tantalizing patterns, and a lot of uncertainty. The upcoming observation windows after perihelion will be critical. If those geometric plasma patterns persist, if they correlate with trajectory changes, if spectroscopy reveals anything anomalous, the case for something extraordinary strengthens. If the patterns disappear, if the spectrum looks boringly normal, If the trajectory settles into predictable behaviour, then we chalk this up to incomplete early data and move on. Either way, the waiting is the hardest part. We're in the moment before the answer arrives, and that moment feels suspended in amber. Part 4. Hidden perihelion and solar conjunction window. Perihelion is the moment of closest approach to the Sun. For 3i Atlas, that moment arrives in late October 2025. At perihelion, the object will be scorched by solar radiation, far more intense than anything it experienced during its interstellar journey. If it's an icy comet, this is when activity peaks. Sublimation rates skyrocket. The coma expands dramatically. If there were any dormant volatiles buried beneath surface dust, this is when they wake up. Perihelion is also when trajectory changes become most effective. A small thrust applied when you're deep in the Sun's gravity well produces a larger change in orbital energy than the same thrust applied farther out. It's basic orbital mechanics. If you were going to maneuver an interstellar object, perihelion is when you'd do it. Solar conjunction complicates everything. From Earth's perspective, as 3i Atlas rounds the Sun, it will appear to move behind our star. The geometry depends on the exact orbital plane and timing, but for several weeks, possibly longer, the object will be unobservable from Earth. The Sun's glare drowns out everything nearby. Even space telescopes like Hubble can't safely point close enough to the Sun to track objects in conjunction. You risk damaging sensitive instruments. There are specialized solar observatories, coronagraphs designed to block the Sun's disk and reveal the surrounding corona, but they're optimized for looking at the Sun itself, not faint moving objects. This creates a blind window. If anything happens during that window, we won't see it happen in real time. We'll only see the consequences when 3i Atlas emerges on the other side. Imagine watching a magician perform a trick. They show you a ball in their hand, move the hand behind their back for a moment, and when it comes back into view, the ball is gone. You didn't see what happened. You only see the before and after. That's our situation. Before conjunction, we have observations of 3i Atlas on a certain trajectory. After conjunction, we'll observe it again. If the trajectory has changed in a way that can't be explained by known forces, we'll know something happened behind the Sun, but we won't know exactly what. Past examples make this scenario less far-fetched than it sounds. Comet Lovejoy, not to be confused with several other comets discovered by Terry Lovejoy, passed extremely close to the Sun in 2011. It was a sun-grazing comet expected to disintegrate. Observations showed it approaching perihelion, then it vanished into the solar glare. When it emerged, it was still intact. Comet Eson in 2013 was another sun-grazer. Predictions varied on whether it would survive. It didn't. It broke apart during perihelion passage. The point is that major changes can happen to objects when they're close to the Sun and out of our view. For 3i Atlas, the stakes are different. This isn't about survival, it's about trajectory. If the reported offset is real and growing, the trajectory is already deviating from predictions. The blind window gives an opportunity for that deviation to amplify in ways we can't monitor. Suppose the object is outgassing asymmetrically, and the outgassing suddenly intensifies at perihelion. The thrust from those jets could alter the orbit significantly. When we see it again, the ephemeris might be wildly wrong. Or suppose, in the more speculative scenario, the object is under intelligent control and its operators choose perihelion as the moment to execute a major course correction. The maneuver happens behind the Sun, unseen. By the time we can observe again, the deed is done. Observatories are well aware of the conjunction problem. They plan around it. For important targets, they try to gather as much data as possible before conjunction and immediately after. Sometimes they coordinate with spacecraft or observatories positioned at different points in space where the geometry is more favourable. For example, spacecraft like Stereo, which orbit the Sun at different locations than Earth, can sometimes observe objects during Earth's conjunction periods. Whether any such coordination is happening for 3i Atlas isn't publicly documented. If it is, those observations could provide crucial continuity across the blind window. The timing also matters psychologically. If you're an observer who believes you're seeing signs of anomalous acceleration, and you know the object is about to disappear from view for weeks, urgency spikes. You push for more observations. You reach out to colleagues. You try to get telescope time on bigger instruments. Because once it's gone, once it's behind the Sun, the opportunity to gather pre-maneuver data is over. You're left analysing whatever you managed to collect beforehand and hoping it's enough to answer your questions when the object reappears. In the scenario where 3i Atlas fires thrusters or undergoes a major outburst during conjunction, the signature would show up in post-conjunction astrometry. The object wouldn't be where the pre-conjunction orbit predicted. The offset could grow to millions of kilometers, maybe tens of millions, depending on the magnitude and duration of the thrust. Radial velocity measurements, if possible, would show unexpected motion toward or away from the Sun. Proper motion across the sky would deviate from projections. All of this is measurable, but only after the fact. You can't catch the maneuver in the act if it happens in the blind zone. There's a darker thought lurking beneath all this. What if the timing isn't coincidental? What if whoever or whatever is piloting 3i Atlas, in the speculative engineered scenario, knows about solar conjunction and uses it deliberately? If you were navigating an interstellar probe through someone else's solar system, and you wanted to change course without being observed, you'd wait until you were obscured from their view. It's the perfect cover. The civilization watching you from their planet can't see behind their own star. They'll notice you've changed trajectory after the fact, but they won't see how you did it, or how much thrust you used or what direction you went. You maintain operational security even while operating in plain sight. Or maybe this is all paranoid speculation built on quicksand. Maybe 3i Atlas is a perfectly normal comet that will pass perihelion, undergo predictable outgassing, and emerge exactly where orbital mechanics says it should be. Maybe the reported offset will be explained by systematic error or misidentification. Maybe in a few months. This will be a footnote in the annals of astronomical anomalies that turned out to be nothing. The only way to know is to wait and watch. Wait for perihelion, wait through conjunction, wait for 3i Atlas to emerge on the other side. Then we check the data. Then we compare predictions to observations. Then we either breathe a sigh of relief or face the reality that something unprecedented just happened 70 million kilometers from Earth, while we watched helplessly from the wrong side of the Sun. We may not see the action live, but soon we'll see the aftermath. Part 5. Why this matters. Paradigm shift potential. Suppose the data holds up. Suppose after perihelion and conjunction, multiple independent observers confirm that 3i Atlas has deviated from its predicted orbit by amounts that cannot be explained by solar radiation pressure, outgassing models, or any known natural mechanism. Suppose spectroscopy reveals anomalies. Suppose the trajectory analysis points unambiguously to some form of active propulsion. What then? If this object is under intelligent control, if it's engineered, if it's a probe or ship or artifact from another civilization, we've just detected the first confirmed extraterrestrial technology in human history. Not a radio signal that might be noise, not a suspicious megastructure that could be dust, an object physically present in our solar system that is moving in ways requiring intelligence. The implications cascade outward in every direction. For SETI, the search for extraterrestrial intelligence, this would represent a paradigm shift. SETI has historically focused on electromagnetic signals, radio telescopes listening for patterns that can't be natural, optical searches looking for laser pulses. The assumption is that intelligent civilizations broadcast intentionally or leak signals into space that we can detect. But what if the first sign of intelligence isn't a message? What if it's motion? What if instead of waiting to hear from them, we notice them by the way they navigate? Trajectory analysis as SETI, astrometry as the new frontier. It forces us to rethink what a signal looks like. Policy and risk frameworks would have to be invented on the fly. Who coordinates the investigation of an engineered interstellar object? NASA has planetary defense protocols for asteroids that might impact Earth. Those protocols don't cover visitors that are steering themselves. The United Nations Office for Outer Space Affairs coordinates international space activities, but has never dealt with confirming extraterrestrial technology. Would there be an emergency committee? Would governments classify the data? Would they share it openly? The tension between scientific transparency and national security interests would be immense. Then there's the public reaction. How do you communicate this? If the announcement comes from reputable institutions with solid evidence, it would dominate news cycles for months. Press conferences, congressional hearings, international summits. If it leaks out through amateur networks and independent researchers before official confirmation, you risk a chaotic information environment where speculation and conspiracy theories drown out facts. Either way, public imagination ignites. Some people would see it as humanity's awakening moment. Proof we're not alone. validation for decades of speculation. Others would see it as threat, an unidentified craft from unknown origins moving through our solar system without asking permission. Fear and wonder compete for headspace. Philosophically, the discovery would alter humanity's self-conception. For all of recorded history, we've been alone as far as we could tell. The universe seemed silent. We built civilizations, science, art, philosophy, all under the assumption that we're the only ones asking questions. If 3i Atlas is artificial, that assumption dies. Someone else is out there. They built something capable of crossing interstellar distances. They sent it here or near here for reasons we can't know. Are they exploring? Surveying? Did they send this probe 1,000,000 years ago, or 10,000, or last century? Is it autonomous, or controlled remotely? Does it even care that we're here? The questions multiply faster than answers ever could. On the flip side, if the anomaly evaporates under scrutiny, if the offset is debunked as measurement error or explained by conventional physics, what then? We learn something important about the limits of our certainty. We learn that astrometric precision at extreme distances with moving objects is harder than we thought. We learn that early data from new discoveries can be misleading. We learn that excitement and bias can push us toward conclusions before evidence justifies them. These are valuable lessons, if humbling. Science corrects itself. The question is whether we correct ourselves before or after making bold public claims. Historical comparisons provide context. Tabby's star, KIC 8461852, showed bizarre dimming patterns that led to speculation about alien megastructures. Years of follow-up observations pointed toward dust as the explanation. Fast radio bursts were once mysterious and potentially artificial until repeating bursts and host galaxy identifications revealed their natural astrophysical phenomena, probably from magnetars. Pulsar signals, when first discovered in 1967, were jokingly called LGM signals for little green men before their natural explanation became clear. Astronomy has a history of anomalies that spark wild hypotheses before mundane explanations emerge. But sometimes the anomaly stays anomalous. The WOW signal from 1977 remains unexplained. No confirmed repeat, no identified source. It fits the profile of an artificial signal, but without repetition, you can't confirm it. Oumuamua, the first confirmed interstellar object, showed acceleration that sparked debate. Natural outgassing, hydrogen icebergs, solar sail artifact. The question hasn't been definitively settled. Anomalies can linger unresolved, neither proven extraordinary nor fully explained naturally. We might be entering that territory with 3i Atlas. The broader theme here is cosmic humility. We thought we knew how to detect intelligence. We thought signals were the key. Maybe we were wrong. Maybe intelligence leaves footprints in dynamics, in motion, in the way objects behave under forces. Maybe the galaxy is full of probes and ships moving through star systems, and we never noticed because we weren't looking at trajectories as data. Or maybe we're overinterpreting noise. Maybe the universe is exactly as indifferent as it always seemed, and our pattern-seeking brains are finding design where there's only chaos. Either resolution, artificial or natural, teaches us about ourselves as much as the cosmos. If artificial, we're forced to confront our place as one voice among many. If natural, we're reminded that certainty is elusive and measurements are always provisional. The stakes feel enormous because they are. Discovery of extraterrestrial technology would be the biggest scientific finding in human history. Confirmation that we let excitement cloud our judgment would be a cautionary tale for the ages. We're in the space between those outcomes, suspended in uncertainty. So far, what you've seen is the stage. But now we peel back the layers. What is normal behavior for an interstellar object? What errors might lurk beneath the data? What wild hypothesis might yet survive scrutiny? The investigation deepens from here. Part 6. Comet Interstellar Object Baseline. What normal looks like. Before we can decide if 3i Atlas is extraordinary, we need a baseline. What does normal look like for objects visiting from interstellar space? We have exactly 2 confirmed examples before this one. The first interstellar visitor, designated 1i/Oumuamua, arrived in October 2017. The name is Hawaiian, roughly meaning scout or first messenger. It was discovered by the Pan-STARRS telescope in Hawaii after it had already passed perihelion and was heading back out of the solar system. Oumuamua was strange from the start. Its shape appeared highly elongated, like a cigar or pancake. based on how its brightness varied. Its surface was reddish. Radiation darkened like objects in the outer solar system. It showed no signs of a coma or tail, no detectable outgassing, yet it exhibited a small but measurable, non-gravitational acceleration as it moved away from the Sun. That acceleration sparked years of debate. Without visible outgassing, what was pushing Oumuamua? Some scientists proposed that even though no coma was visible, tiny amounts of gas could still be venting below detection thresholds, but sufficient to create thrust. Others suggested more exotic explanations. Maybe it was a hydrogen iceberg, frozen molecular hydrogen sublimating without leaving observable traces. Maybe it was an artificial light sail, a thin reflective structure pushed by solar radiation pressure. That last hypothesis came from respected scientists, not fringe theorists, though it remained controversial. No consensus emerged. Oumuamua accelerated away into the darkness before we could study it thoroughly, leaving more questions than answers. The second visitor, 2I/Borisov, arrived in August 2019 and behaved much more conventionally. Borisov looked like a comet. It had a coma, it had a tail. Spectroscopy showed water, carbon monoxide, and other typical cometary volatiles. Its nucleus was a few hundred meters across, unremarkable in size. The orbit clearly indicated interstellar origin, but everything else about Borisov screamed normal comet. It followed predictable outgassing models. Its brightness varied as expected. When it fragmented near perihelion, that too fit standard comet behavior under thermal stress. Borisov was almost boring, which in this context was reassuring. It proved that interstellar comets can be ordinary, that not every visitor needs to be weird. Cometary outgassing physics is well studied because we've observed thousands of comets. When ice sublimates, it doesn't happen uniformly across the surface. Some areas are more active than others due to composition differences, dust coverage, or exposure to sunlight. Active regions create jets of gas and dust streaming into space. If those jets are asymmetric, if one side of the nucleus is more active than the other, the escaping material carries momentum away, and the nucleus recoils in the opposite direction. It's Newton's third law: action and reaction. Over weeks and months, this tiny thrust accumulates into measurable orbital changes. Orbit-fitting software accounts for this by including non-gravitational acceleration parameters in the model. The most common formulation uses a 1 for radial acceleration, directly toward or away from the Sun, and a 2 for transverse acceleration, perpendicular to the Sun object line. These coefficients are fitted from astrometric observations along with the standard orbital elements. For typical comets, A1 values range from 10 to the negative 10 to 10 to the negative 7 astronomical units per day squared. Those numbers are tiny. To give you a sense of scale, 10 to the negative 8 AU per day squared translates to roughly 1/10 millionth of Earth's surface gravity. Yet integrated over months, it's enough to shift an orbit by thousands or tens of thousands of kilometers. For 3I Atlas to deviate by 1 million kilometers over the span of a few months, the required acceleration would be at the high end of what's been observed for any comet, possibly beyond. You'd need either extremely vigorous outgassing sustained continuously, or a much larger effective force than sublimation typically produces. Extremely vigorous outgassing should be visible. The coma should be enormous. Brightness should spike. Observers should see dramatic jets in high-resolution images. If those signatures are absent or weak, the outgassing explanation struggles. Dust plays a role too. When gas jets carry dust particles away from the nucleus, the dust reflects sunlight and makes the coma visible, but dust also creates drag. As gas molecules zip away at high speed, they collide with dust grains and transfer momentum. The dust slows the gas down slightly, and the reaction force affects the nucleus. Modelling this requires knowing the dust-to-gas ratio, the size distribution of dust particles, and the ejection velocities. All of these parameters are uncertain for a newly discovered object observed from millions of kilometers away. Solar heating creates thermal lag effects. The nucleus rotates, so the subsolar point, the spot directly facing the Sun, moves around. But heat doesn't penetrate the surface instantly. There's a delay between when a region is heated and when it reaches maximum outgassing. This lag means the peak outgassing doesn't happen at noon local time on the comet, but some hours later. That offset creates a torque that can change the spin state and introduces complexities in the thrust direction. For slow rotators, the effect is different than for fast rotators. Without knowing 3i Atlas's rotation period, modelling these effects accurately is guesswork. Compare the magnitude of forces involved. Solar radiation pressure on 3i Atlas depends on its cross-sectional area and reflectivity. For a spherical object a few kilometres in diameter with typical cometary albedo, around 5 to 10%. Radiation pressure creates an acceleration on the order of 10 to the negative 9 to 10 to the negative 8 AU per day squared. Similar magnitude to outgassing for a quiet comet, but much smaller than what's needed to explain a 1,000,000 kilometre deviation. You'd need an object with huge surface area relative to its mass, like a sail, or you'd need something else entirely. Spectral signatures tell us about composition. Water ice is the most abundant volatile in most comets, and when it sublimates, the resulting water molecules get dissociated by ultraviolet light into hydrogen and oxygen. Hydroxyl radicals, OH, produce strong emission lines that are easy to detect. Carbon monoxide sublimates at lower temperatures than water, so it becomes active farther from the sun. Comets approaching from the outer solar system often show CO emission first, then water kicks in as they get closer. If 3i Atlas is rich in CO and shows strong CO emission, that could drive significant outgassing even at large distances where water would still be frozen. Some comets fragment. Thermal stress or rotational stress can crack the nucleus, splitting it into multiple pieces. Fragmentation events release a lot of dust and gas suddenly, creating a burst of brightness, and potentially a thrust if the breakup is asymmetric. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before impacting Jupiter. Comet Schwarzmann-Wachmann 3 has undergone multiple fragmentations over decades. If 3i Atlas fragmented, that could explain sudden changes in trajectory or brightness. However, fragmentation usually leaves visible evidence. You see multiple nuclei in images. The morphology changes dramatically. Observers would have noticed. So where does 3i Atlas sit on this spectrum? If it's behaving like an extreme version of a jet-active comet, we need evidence of extreme activity. Brightness far exceeding predictions, massive coma, strong emission lines in spectra, jets visible in high-resolution images. If all of that is present, the outgassing explanation works, even if the magnitude is at the edge of what's been seen before. Comets are diverse. Maybe 3i Atlas is just a bizarre outlier, a hyperactive comet from an interstellar environment with composition we've never encountered. If that evidence is absent, if the object appears relatively quiet despite the alleged trajectory deviation, then outgassing doesn't explain it. You're left searching for alternative mechanisms or reconsidering whether the trajectory deviation is real at all. The baseline tells us what's possible within known physics. The question is whether 3i Atlas fits inside that envelope or breaks through it into uncharted territory. Part 7. Astrometry. Ephemeris modelling and error sources. Measuring the position of a moving object millions of kilometres away sounds straightforward. Point your telescope, take an image, identify the object, measure its coordinates. In practice, it's a minefield of potential errors. Astrometry, the precise measurement of positions and motions of celestial objects, requires accounting for dozens of systematic effects. Any one of them, if mishandled, can introduce biases that look like real motion when they're actually artifacts. Start with the imaging itself. A telescope collects light from stars and your target object onto a detector, typically a CCD camera. The detector has pixels arranged in a grid. You take an exposure, and each pixel records how many photons hit it. Your target appears as a cluster of bright pixels against a background of stars. To measure its position, you find the centroid, the brightness-weighted center of those pixels. This process is called centroiding, and it's sensitive to noise. If the object is faint, if the background sky is bright, if there are hot pixels or cosmic ray hits nearby, the centroid calculation can be thrown off. A few pixels error translates to arcseconds on the sky. Arcseconds translate to thousands of kilometers at the distance of 3i Atlas. Reference stars provide your coordinate grid. You identify stars in the image whose positions are known precisely from a catalogue, typically Gaia. The Gaia Space Telescope has measured positions for billions of stars with micro-arcsecond precision. You match the stars in your image to the Gaia catalogue and use them to establish a transformation from pixel coordinates to sky coordinates. This transformation accounts for the telescope's plate scale, how many arcseconds per pixel, and any rotation or distortion in the image. If your reference stars are too few, or if they're in the wrong part of the image, the transformation becomes uncertain. If the Gaia catalogue itself has errors for those particular stars, perhaps because they're variable or binary, those errors propagate into your target's position. Optical distortion is a killer. No telescope produces a perfectly flat, undistorted image. Lenses and mirrors introduce aberrations. The image is stretched or compressed differently in different parts of the field of view. Professional observatories spend considerable effort characterizing these distortions. They image dense star fields, compare measured positions to catalogue positions, and build distortion maps. If you're using a telescope without a good distortion model, or if you're observing near the edge of the field where distortion is worst, your measurements are systematically wrong. Atmospheric refraction bends light as it passes through Earth's atmosphere. The amount of bending depends on the wavelength, the air temperature, the atmospheric pressure, and the altitude of the object above the horizon. An object low on the horizon appears higher than it actually is, because refraction bends the light path upward. If you don't correct for this, your measured position is off. Standard refraction models exist, but they assume a standard atmosphere. If the actual atmospheric conditions differ, the correction is imperfect. Turbulence, seeing, also blurs the image, spreading the light over more pixels and making centroids less precise. Timing matters. You need to know exactly when the image was taken to compare the measured position to an ephemeris prediction. Telescope clocks can drift. If the timestamp on your image is off by minutes or hours, the predicted position you're comparing to is for the wrong moment, and you'll see a fake offset. Light travel time corrections matter too. The light you see from 3i Atlas left the object some number of minutes ago depending on its distance. The position you calculate needs to be corrected for where the object was when the light was emitted, not where it appears now. For fast-moving objects, this correction can be tens of arcseconds. Parallax adds complexity. Different observers on Earth see the object from slightly different angles depending on their location. An observer in North America and an observer in Australia are separated by thousands of kilometers, and that baseline creates parallax shifts on the order of arcseconds for nearby objects. 3i Atlas is far enough that parallax is small, but it's not zero. If you're combining observations from multiple observatories without correcting for parallax, you introduce spurious position differences. Detector effects can be insidious. Charge transfer efficiency in CCDs, how well electrons move from pixel to pixel when read out, can introduce position-dependent errors. Bad columns or rows on the chip that aren't properly masked create artifacts. Flat field calibration, correcting for uneven sensitivity across the detector, affects brightness measurements, which in turn affects centroids if you're doing weighted averaging. Electronic ghosts or scattered light from bright stars create fake sources or halos that confuse the centroiding algorithm. Now consider amateur observers. They're using smaller telescopes, often with less precise mounts and less sophisticated calibration. They might be imaging from light-polluted sites. Their reference catalogues might be outdated or low precision. Their software might use simplified algorithms that work for bright objects but struggle with faint ones. None of this means amateurs can't do good astrometry. Many do, and their contributions are valuable, but the potential for systematic error is higher. If the reported offset for 3i Atlas comes primarily from amateur data, professional skepticism is warranted. Orbital fitting software tries to estimate all these uncertainties. Programs like OrbFit or the JPL Orbital Determination System take astrometric measurements with their associated uncertainties and fit an orbit that best matches the data. The output includes not just the orbital elements, but also covariance matrices and uncertainty ellipses. These tell you how confident the fit is. If the residuals, the differences between observed and fitted positions, are randomly scattered around zero, the model is good. If residuals show a trend, increasing or decreasing systematically over time, the model is missing something. Either there's a real acceleration not included in the model, or there's a systematic error in the measurements. For the million-kilometre offset claimed for 3i Atlas, you have to ask whether any plausible systematic error could produce that. Suppose all the observations used a star catalogue with positions off by half an arcsecond in one direction. That's a huge catalogue error, much larger than Gaia's, but humour the scenario. Half an arcsecond at the distance of 3i Atlas translates to roughly 30,000 kilometres, not enough to explain a million. You'd need multiple independent systematic errors all conspiring in the same direction. Or you'd need a massive blunder like using the wrong epoch for the reference stars, so the catalogue positions are from years earlier and proper motions haven't been accounted for. That's possible, but easily checked. Historical precedents exist where apparent orbital anomalies turned out to be measurement artifacts. Asteroids occasionally get misidentified. Two separate observations thought to be the same object are actually different objects, and trying to fit a single orbit through both creates impossible residuals. That's called linkage error, and it's more common with faint objects discovered in crowded star fields. For 3i Atlas, which is bright enough and well-tracked, linkage error seems unlikely, but you can't rule it out entirely without verifying every single observation independently. Another historical case involved comet positions measured relative to a planetary satellite. Observers thought they were measuring the comet's position relative to background stars, but due to a pointing error, they were actually measuring relative to one of Jupiter's moons. When they corrected the error, the comet's apparent motion changed dramatically. Mistakes like that are rare but not impossible. Vigilance is required. So what's the conclusion? If the offset is real, if it survives scrutiny and independent verification, then measurement error isn't the answer. If multiple observers using different telescopes, different detectors, different reference catalogues, all independently measure positions that deviate from the ephemeris in the same way, systematic error becomes implausible. The errors would have to be perfectly correlated, which they shouldn't be. On the other hand, if only one or two observers see the offset, or if their methods can't be verified, error remains the leading hypothesis. Until we see confirmation from professional observatories with robust calibration and peer-reviewed methodology, the jury is out. Astrometry is hard. Getting it right requires care, expertise, and cross-checks. Rushing to conclusions based on early data is a recipe for embarrassment. Part 8. Hypotheses for the anomaly, natural versus engineered. Let's lay out the possibilities in stark terms. If the trajectory offset is real, something is accelerating. 3i Atlas beyond what gravity and radiation pressure predict. We can organize hypotheses into two broad categories, natural and engineered. For each, we need to ask whether the required forces are physically plausible, whether they'd leave observable traces, and how likely each scenario is given what we know. Natural hypotheses start with extreme outgassing. Imagine 3i Atlas has an unusually volatile rich composition. Maybe it formed in a molecular cloud with high concentrations of carbon monoxide, or some even more volatile species. As it approaches the sun, sublimation kicks in early and hard. Gas jets fire continuously, creating sustained thrust. To generate enough acceleration to produce a 1,000,000-kilometer deviation over a few months, you'd need mass loss rates far higher than typical comets. The nucleus would be shrinking noticeably. Brightness should increase dramatically as the coma expands. We should see that in photometric data. If we don't, this hypothesis struggles. Volatile cliff collapse is a variant. Suppose the surface is covered in layers of dust and ice, insulating deeper, more volatile ices. Suddenly, thermal stress cracks the surface layer, exposing the fresh ice beneath. A massive outburst occurs, releasing huge amounts of gas and dust in a short time. The impulse changes the trajectory. This has been observed in some comets. Comet Holmes underwent a dramatic brightening outburst in 2007, increasing in brightness by a factor of 1,000,000. If 3i Atlas did something similar, we'd see it as a brightness spike followed by decay as the outburst subsides. Has that been reported? Not prominently, which casts doubt on this mechanism. Jet fragmentation offers another angle. If the nucleus is rotating and jets fire from specific active regions, the thrust vector changes as the object spins. If the rotation is chaotic due to an irregular shape and uneven mass distribution, the net thrust over time could be complex and hard to predict. Maybe the standard orbit models assume a simpler outgassing pattern than actually exists. Fitting better models with more parameters might capture the behavior. This would still be natural, just poorly modeled. The test is whether better models, once developed, can fit the data without invoking exotic physics. Solar-wind interaction is usually negligible for comets, but maybe not always. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the sun. When these particles hit a comet's coma, they ionize gas molecules and create drag. For a typical comet, this drag is tiny compared to outgassing thrust. But suppose 3I Atlas has an unusually large diffuse coma with low gas density. The solar wind coupling might be enhanced. Or suppose there's a coronal mass ejection, a burst of solar wind far denser than usual, that happens to hit 3I Atlas at the right time. The impulse could perturb the trajectory. This would be a rare event, hard to predict, but not impossible. Micro-impacts are the long-shot natural hypothesis. Space isn't perfectly empty. There are dust grains, tiny particles left over from comets and asteroids. If 3I Atlas happens to plough through a localized cloud of such particles, the impacts could impart momentum. This mechanism is invoked sometimes for very small perturbations, but scaling it up to explain a 1,000,000-kilometre offset seems implausible. The particle density required would be enormous, and we'd likely see evidence of collisional heating or changes in the object's brightness. Now, the engineered hypotheses. Suppose 3I Atlas isn't entirely natural. Suppose it's partially or wholly constructed. A passive solar sail is the simplest version. Imagine a large, thin structure, like a sail or parachute, attached to or part of the object. Sunlight pushes on this sail, creating continuous acceleration. The sail doesn't need power, it's just reflective material deployed in space. Humanity has built solar sails, the Japanese Icaros spacecraft, the Planetary Society's light sail, NASA's Near-Earth Asteroid Scout. All use solar radiation pressure for propulsion. The thrust is minuscule, but over interstellar timescales it adds up. If 3I Atlas is a light sail from another civilization, sent on a multi-thousand-year journey, radiation pressure could be steering it. The problem is that sails are hard to hide. They're large and reflective. We should see them in images as extended structures. If 3I Atlas looks like a point source, a sail seems unlikely unless it's edge-on or retracted. Active propulsion means onboard engines. Ion drives use electric fields to accelerate ions to high speed, producing thrust. Hall thrusters and gridded ion engines are variants. These are real technologies we use on spacecraft. Thrust levels are low, millinewtons, but efficient. You can run them continuously for months or years if you have enough power. Where does the power come from? Solar panels if you're close enough to a star. Radioisotope thermoelectric generators if you're farther out. Or something more exotic like fusion or antimatter if we're speculating about advanced technology. An ion engine leaving a plume of ionized gas might create the geometric glow patterns observers claim to see. The plume would be directional, aligned with the thrust vector, and localized near the engine nozzles. If you're firing multiple thrusters in a controlled pattern to steer, you'd get multiple glow zones. A hybrid scenario combines natural and engineered elements. Maybe 3I Atlas is mostly natural, a comet nucleus, but with small artificial devices embedded in it. Thrusters or sensors or other equipment placed by an interstellar probe that intercepted the comet long ago. The bulk of the mass is ice and rock, but the technology is guiding it. This lowers the power requirements because you're not pushing a massive spacecraft. Just nudging a comet slightly. It also provides camouflage. From a distance, it looks natural until you examine its behavior closely. Intelligent control is the boldest hypothesis. The trajectory isn't random, it's deliberate. Whoever built 3I Atlas programmed it to reach a specific perihelion distance, maybe to study the Sun, or to pass near Earth for observation, or to rendezvous with something else in the solar system. The course corrections are planned maneuvers, not random drift. This implies an onboard computer or remote control from a distant sender. It implies purpose and intention. It implies we're not alone. Evaluate each hypothesis by the required energy. To change velocity by hundreds of meters per second, which is roughly what's needed for the reported offset, you need kinetic energy. For a 1,000-ton object, that's on the order of 10 to the 14 joules. Outgassing from sublimating ice releases latent heat, roughly 3 times 10 to the 5 joules per kilogram for water ice. You'd need to sublimate hundreds of thousands of tons of ice to supply that energy through outgassing thrust. Is the nucleus big enough? If it's a few kilometers across with typical comet density, total mass is maybe 10 to the 12 kilograms. Sublimating 0.1% of that gives you the required mass, so it's plausible, barely. An ion drive running for months at millinewton thrust levels accumulates the same velocity change. The energy comes from the power source. A kilowatt-class ion drive running for 100 days consumes roughly 10 to the 12 joules, much less than the kinetic energy delivered because ion drives are efficient. so active propulsion is energetically feasible too. Occam's razor suggests natural explanations should be preferred unless they definitively fail. Engineered scenarios require assuming the existence of other civilizations, interstellar travel capability, and presence in our solar system. Those are huge assumptions. But Occam's razor isn't a physical law. If the data can't be explained naturally, you're forced to consider alternatives. The history of science includes cases where the simplest explanation turned out to be wrong. Continental drift was dismissed for decades because the mechanism wasn't understood. The reality was more complex than the simple models allowed. What observations would discriminate between hypotheses? Spectroscopy looking for exotic elements or isotope ratios inconsistent with natural formation. Metals in unusual oxidation states. Emission lines from plasma at temperatures too high for cometary comas. Time-resolved astrometry catching the acceleration in action, showing impulsive changes corresponding to thruster firings. High-resolution imaging revealing structures that don't look like rock and ice. Polarimetry that indicates artificial materials. Radio emissions if there's onboard electronics. Heat signatures if there's a power source. Any of these would tip the scales toward engineered. Their absence doesn't prove natural, because a sufficiently advanced probe might not leak obvious signals. But it makes natural more likely. We're in the phase before discrimination. We have suggestive patterns but not definitive proof. The trajectory anomaly, if real, demands explanation. The plasma glow claims, if confirmed, demand explanation. But demand doesn't equal delivery. Sometimes nature is stranger than we expect, and what looks engineered is just an edge case we haven't encountered before. Sometimes our instruments mislead us, and what looks real is illusion. And sometimes, rarely, the universe surprises us in ways that overturn everything we thought we knew. The only way forward is more data, better observations, and rigorous skepticism directed at every hypothesis equally. Part 9. Controversies, Conspiracies, and Hidden Data. The claim originates from an independent researcher publishing on Medium. Medium is a blogging platform, not a peer-reviewed journal. Anyone can publish there. That doesn't automatically invalidate the work, but it does change the scrutiny applied. Peer review exists for a reason. Experts in the field read your paper, check your methodology, look for errors, and decide whether your conclusions are supported by evidence. Medium bypasses that process. The author is making their case directly to the public, which can be good for rapid dissemination but bad for quality control. Who is this researcher? What's their background? Do they have formal training in astronomy and astrometry? Have they published credible work before? These questions matter. A seasoned amateur astronomer with decades of experience and published discoveries has credibility. Someone with no track record making extraordinary claims has less. The article reportedly includes data, astrometric measurements, timestamps, residuals. That's good. It means the work can be checked. Other people can take the same data, run their own analysis, and see if they reach the same conclusions. Has anyone done that? Have other amateur or professional astronomers attempted to replicate the findings? If multiple independent groups confirm the offset, credibility rises. If no one can replicate it, or if attempts to replicate reveal flaws in the original analysis, credibility collapses. The professional astronomy community's silence is conspicuous. No astronomer's telegram has addressed 3i Atlas trajectory anomalies. Astronomers' telegrams are short, fast turnaround notices used by professionals to communicate discoveries or interesting phenomena. They're not peer-reviewed, but they're vetted by editors. If a major observatory confirmed a 1,000,000-kilometre trajectory offset, you'd expect an A-tell. The absence might mean the professionals haven't looked closely yet, or that they have looked and found nothing worth reporting. Silence is ambiguous. Could there be institutional caution? Absolutely. Imagine you're an astronomer at a major institution. You see claims online that an interstellar object is maneuvering. You know that if you issue a public statement and turn out to be wrong, your reputation takes a hit. You know the media will sensationalize it. You know conspiracy theorists will latch onto any ambiguity. The safest move is to stay quiet until you're certain. Gather more data. Run multiple independent analyses. Check and recheck. Only then, if the anomaly holds, do you go public. This cautious approach protects individuals but delays information reaching the public. It's the trade-off between rigour and speed. Alternatively, maybe there's active suppression. Not in the conspiratorial sense of shadowy agencies hiding evidence, but in the softer sense of gatekeeping. Maybe an astronomer submitted a paper about the anomaly to a journal, and reviewers rejected it because the claims were too extraordinary or the evidence too preliminary. Maybe observing time proposals to study 3I Atlas with major telescopes were declined because the anomaly wasn't considered credible enough. These are institutional barriers, not secret conspiracies, but they have the effect of slowing or preventing information from entering the official scientific record. Is the data publicly available? This is crucial. Open science principles say that data underlying major claims should be accessible so others can verify. If the astrometric measurements, raw images, and analysis code are posted somewhere like GitHub or the Minor Planet Center's database, anyone can audit the work. If they're proprietary or only mentioned in summary form, verification is impossible. The credibility of the claim depends heavily on transparency. Scientists don't trust black boxes. They trust reproducible, transparent analysis. Historical comparisons help calibrate expectations. The Pioneer anomaly, a tiny unexplained acceleration of the Pioneer spacecraft detected in the 1990s, sparked years of investigation. Eventually, it was explained by anisotropic thermal radiation from the spacecraft itself. Not exotic physics, just careful bookkeeping. The WOW signal, a strong narrowband radio signal detected in 1977, has never been explained or repeated. It remains tantalizing but unconfirmed. Tabby's star, with its bizarre dimming patterns, generated massive public interest and speculation about alien megastructures. Years of follow-up pointed to dust, probably from a disintegrated comet, as the culprit. The pattern is clear. Anomalies grab attention, speculation runs wild, and more often than not, mundane explanations emerge. But not always. Fast radio bursts were discovered in 2007 and initially mysterious. Some speculated artificial origins. Over time, multiple repeating FRBs were found, host galaxies identified, and the phenomena traced to magnetars, exotic neutron stars with extreme magnetic fields. Natural, but exotic and not fully understood. Pulsar signals, when first detected by Jocelyn Bell and Anthony Hewish in 1967, were so regular they were jokingly labelled LGM for little green men. Turned out to be rotating neutron stars emitting beams of radio waves, natural but unlike anything expected. The point is that nature can surprise us, and occasionally, anomalies resist simple explanation for years. Could citizen astronomers independently verify the 3I Atlas offset? In principle, yes. Amateur networks like the American Association of Variable Star Observers or the International Occultation Timing Association coordinate observations. If a call went out for people with suitable equipment to measure 3I Atlas positions and report them, you'd get data from dozens of observers worldwide. Aggregate that data, apply proper calibration and error analysis, and you'd have a robust check. The challenge is organizing it and ensuring data quality. Not all amateur data is created equal. But crowdsourced science has worked before. Citizen scientists discovered exoplanets in Kepler data, classified galaxies in Galaxy Zoo, and tracked asteroids through spacewatch programs. The internet amplifies both signal and noise. On one hand, it lets independent researchers share findings instantly, bypassing traditional gatekeepers. On the other, it spreads misinformation, speculation, and hype at the same speed. Distinguishing credible analysis from wishful thinking becomes harder when everything looks equally authoritative on a screen. The Medium article could be groundbreaking citizen science or amateur overreach. Without independent verification, we can't tell. There's a philosophical tension here between democratization of knowledge and expertise-based validation. Should anyone with data and an argument get a hearing, or should claims be filtered through credentialed experts first? The former risks drowning in noise, the latter risks gatekeeping and missed discoveries. Maybe the answer is both. Let anyone publish, but reserve judgment until independent verification occurs. Treat extraordinary claims with interest but not credulity. Stay open to surprise but demand evidence. That's the ideal. In practice, people choose sides. Believers embrace the claim and dismiss skeptics as closed-minded. Skeptics dismiss the claim and accuse believers of gullibility. The polarized discourse obscures the actual question. Is the data good or not? Is this the beginning of grassroots detection of something extraordinary, or amateur error amplified by digital echo chambers? Time and more observations will answer that question. But patience is hard when the stakes feel existential. Part 10. Broader implications and what to watch. Next. Perihelion happens late October 2025. Solar conjunction follows shortly after. For several weeks, 3i Atlas will be unobservable from Earth. When it emerges, probably in late November or December, the race is on. Every major observatory with suitable instruments will be pointing at it, or should be. Which one specifically? The Hubble Space Telescope can provide high-resolution imaging in visible and ultraviolet wavelengths. The James Webb Space Telescope excels in infrared, perfect for detecting heat signatures or spectroscopy of molecules in the coma. Ground-based observatories like the Keck telescopes in Hawaii, the Very Large Telescope in Chile, and the Gemini observatories can obtain spectra and photometry. Radar might be possible if 3i Atlas passes close enough to Earth, though typical radar systems like Arecibo, now collapsed, or Goldstone require targets within a few tens of millions of kilometers. What measurements matter most? Astrometry tops the list. Precise position measurements over time will reveal whether the trajectory continues to deviate from predictions or settles back into expected behavior. If the offset persists or grows post-perihelion, that strongly suggests real acceleration rather than pre-perihelion measurement error. If the offset disappears and positions match predictions, that points toward error or transient effects that have ended. Spectroscopy can identify what gases are present and in what amounts. If unexpected elements appear, metals that shouldn't be in a cometary coma, or isotopes with unusual ratios, that's a red flag. Photometry tracks brightness over time. Sudden changes, periodic variations, or unexpected dimming or brightening patterns can hint at surface features, rotation, or activity changes. Morphological imaging, taking pictures with enough resolution to see structure, matters too. Does the coma show the geometric glow zones that earlier reports claimed? Do those zones move or change shape in ways consistent with jets or inconsistent with natural processes? Polarimetry measures how light is polarized after reflecting off or scattering from the object. Different materials polarize light differently. Dust produces one polarization signature, ice another, metals a third. Anomalous polarization could indicate artificial materials. Specific outcomes that would support active maneuvering include persistent trajectory drift, beyond what any reasonable outgassing model can explain, even models with generous parameter choices. Detection of metals like aluminum, titanium, or rare earth elements in the coma would be bizarre for a natural comet. Emission lines indicating plasma temperatures higher than solar radiation could produce would hint at an energy source. Sudden impulsive changes in velocity, like the object accelerating over a few hours then stopping, would scream propulsion. Post-perihelion trajectory shifts larger than pre-perihelion predictions by orders of magnitude, especially if the new trajectory points toward a specific target like Earth or another planet, would be very hard to explain naturally. Conversely, outcomes supporting natural explanations include brightening and coma expansion, consistent with water and carbon monoxide outgassing, spectroscopy showing typical cometary molecules and nothing else, morphology consistent with a fragmenting or a symmetrically outgassing nucleus, trajectory settling into behavior well modeled by updated non-gravitational acceleration terms with physically reasonable parameters. Essentially, if 3i Atlas starts acting like Comet Borisov, we relax. Where can the public track updates? The Minor Planet Center publishes orbit solutions and observation logs. The Astronomers Telegram website posts short bulletins. NASA's Jet Propulsion Laboratory updates the Horizon system regularly. Space news sites like Space.com, Universe Today, and Sky and Telescope report on major developments. Social media, particularly X, formerly Twitter, hosts a community of professional and amateur astronomers who share findings in real time. Following hashtags related to interstellar objects or specific observatory accounts can provide early alerts. The IAU's Central Bureau for Astronomical Telegrams sometimes issues circulars for significant discoveries. Setting up RSS feeds or alerts for those sources means you'll know within hours when new data drops. Some astronomy forums like Cloudy Nights or the Bad Astronomy Forum on Universe Today have active discussions where people dissect new observations as they arrive. Reddit's astronomy and space communities often aggregate news quickly, though the signal-to-noise ratio varies. For those who want raw data, the Minor Planet Center's database allows searching for specific objects and downloading astrometric observations submitted by observatories worldwide. Future episodes or updates to this investigation will depend entirely on what happens post-conjunction. If 3i Atlas emerges on a drastically different trajectory, a follow-up becomes urgent. We'd need to analyse the new data, compare it to predictions, and assess whether natural explanations remain viable. If it emerges exactly where expected, we discuss what went wrong with the initial claims, what lessons about measurement error and premature conclusions we can extract, and whether anything interesting remains. If the situation stays ambiguous, observations showing anomalies but not definitive enough to confirm anything extraordinary, we'd explore that uncertainty and what additional observations could resolve it. Stakes are high either way. If this is artificial, we've detected the first confirmed extraterrestrial technology. That's not just a scientific discovery, it's a civilizational milestone. It changes how we think about our place in the cosmos, about the prevalence of intelligence, about whether the galaxy is populated or empty. Philosophically, it addresses one of humanity's oldest questions: are we alone? Practically, it raises questions about communication, study, potential risk, and what comes next. Do we try to signal it? Do we just observe? What if it observes back? If this is natural, or if it's measurement error, we learn different lessons. We learn about the diversity of cometary behaviour, about the extremes that natural processes can reach. We learn about the limits of early data from newly discovered objects, about how uncertainties compound, and about the need for patience before making bold claims. We learn about human psychology, how badly we want to find something extraordinary, how easily confirmation bias can creep into analysis. Those lessons are less romantic than discovering alien technology, but they're valuable. Science advances through mistakes corrected as much as through discoveries made. There's also the intermediate scenario where the anomaly is real, but the explanation remains unclear. Maybe 3i Atlas does something no comet has done before, something that strains natural models but doesn't definitively break them. Maybe the data quality isn't good enough to distinguish between extreme outgassing and low-level propulsion. We're left with an unsolved mystery like Oumuamua's acceleration or the WOW signal. Frustrating, but that's how science works sometimes. Not every question gets a neat answer on a convenient timeline. Radar follow-up deserves mention. If 3i Atlas passes within radar range after perihelion, which depends on its exact post-conjunction trajectory, facilities like the Goldstone Solar System radar in California or the Arecibo successor systems could bounce radio waves off it. Radar provides extremely precise distance and velocity measurements. It can also reveal surface texture, rotation rate, and size estimates. Radar images of asteroids have shown double-lobed shapes, surface boulders, and even binary systems. If 3i Atlas has unusual radar properties, like high reflectivity suggesting metal, or geometric shapes inconsistent with natural erosion, that would be significant. Space-based observatories positioned away from Earth might maintain visibility during part of Earth's conjunction window. The Solar and Heliospheric Observatory, SOHO, watches the Sun continuously and has discovered thousands of comets passing close to it. If 3i Atlas passes through SOHO's field of view during perihelion, we'd get observations during the blind window. The Parker Solar Probe and Solar Orbiter missions studying the Sun might catch glimpses depending on geometry. Coordinating observations across multiple platforms maximizes coverage. The resolution, whatever it is, teaches us something fundamental. If artificial, we learn the universe is less empty than we feared. Intelligence arises, builds, explores. The Fermi paradox, the question of why we haven't seen aliens despite the universe being so large and old, gets an answer. We just weren't looking the right way. If natural, we learn that our models are incomplete, that comets and interstellar objects have more tricks than we gave them credit for. Either way, the cosmos reveals more of itself. Either way, we grow in understanding. This is why astronomy matters. Not just for pretty pictures or abstract knowledge, but because occasionally, rarely, the universe hands us a puzzle that forces us to question assumptions. 3i Atlas might be that puzzle. Or it might be a false alarm, but the process of investigating, of gathering evidence, of testing hypotheses, that process is the engine of discovery. every great finding in history looked uncertain at first. Every paradigm shift was resisted before it was accepted. We're in the uncertain phase. Now that we've laid out the anomaly, the hypotheses, what to watch next, let's zoom out. The cosmos is full of surprises unfolding right now. How does 3i Atlas compare to other breakthroughs, other technologies, other speculative science happening across astronomy and physics? Context matters. Let's provide it. Part 11. Recent exoplanet discovery with exotic atmosphere. In August 2025, astronomers announced the discovery of an Earth-sized exoplanet orbiting a red dwarf star 40 light-years away. The planet, designated GJ987c, sits at the inner edge of the star's habitable zone. Habitable zone means liquid water could exist on the surface if conditions are right. That alone isn't extraordinary. We found dozens of such planets. What made GJ987c newsworthy was its atmosphere. The James Webb Space Telescope observed the planet during transits, when it passes in front of its star from our viewpoint. Starlight filtering through the planet's atmosphere gets absorbed at specific wavelengths corresponding to molecules in the air. This technique, transmission spectroscopy, reveals atmospheric composition. GJ987c showed strong absorption lines of methane and ammonia, not unexpected for a planet. But it also showed something odd, a broad absorption feature that didn't match any known molecule. The feature appeared in the mid-infrared, centered around 7 microns, and was far stronger than models predicted. Initial speculation ran wild. Was this an unknown atmospheric molecule, a biosignature, some gas produced by life that we hadn't considered, an artifact of the data reduction? Follow-up observations confirmed the feature. It wasn't noise. Multiple transits showed the same pattern. Chemists and atmospheric modelers went to work trying to explain it. Proposals included complex organic hazes, photochemical products of methane breaking down under ultraviolet light from the star. Others suggested phosphine or some exotic sulfur compound. Phosphine gained attention because it was proposed as a possible biosignature on Venus, though that claim remains controversial. On GJ987c, phosphine would require either geological processes we don't understand or biological production. The debate is ongoing. The parallel to 3i Atlas is striking. In both cases, we observe something in our telescope data that defies easy explanation. In both cases, the immediate question is whether the surprise is natural but poorly understood, or a hint of something deeper. For the exoplanet, natural processes are almost certainly the answer. Atmospheric chemistry is complex, and we've only studied Earth's atmosphere in detail. Exoplanet atmospheres might routinely produce molecules we don't expect. But the parallel shows how scientific skepticism operates. You don't jump to extraordinary conclusions. You exhaust conventional explanations first. How do astronomers verify exoplanet findings? Repeated observations with independent instruments. GJ987c was observed by JWST, then by ground-based telescopes during subsequent transits. Consistency across instruments builds confidence. Modelling comes next. Atmospheric scientists construct models of the planet's temperature structure, photochemistry, cloud formation, and compare predicted spectra to observed spectra. If a model matches the data using only known physics and chemistry, the mystery dissolves. If no model fits, you're forced to consider new molecules, new processes, or new physics. Host star activity matters too. Red dwarfs are active stars. They flare, sending bursts of high-energy radiation toward their planets. They have star spots, cooler regions on the surface that affect the spectrum. If an observation happens during a flare, or when a star spot is in the line of sight, the planet's apparent spectrum can be contaminated. Teasing apart stellar effects from genuine planetary signals requires careful timing and multiple observations. For GJ987c, researchers checked stellar activity logs. No major flares coincided with the transits. Starspot models couldn't reproduce the observed feature. The signal seems planetary. Now pose the rhetorical what-if. Suppose the mystery molecule on GJ987c were engineered. Suppose an advanced civilization terraformed the planet, seeded its atmosphere with gases designed to signal their presence. How would we tell? You'd look for isotope ratios that don't match natural planetary formation. You'd look for concentrations far exceeding equilibrium levels, suggesting continuous production. You'd look for multiple gases in combinations that shouldn't coexist in a natural atmosphere. So far, nothing like that has been found on GJ987c. The mystery molecule, whatever it is, appears at parts per million levels, consistent with natural trace gases. But the thought experiment is useful. It shows that distinguishing natural from artificial isn't always straightforward. Even if we saw clear evidence of atmospheric engineering, proving it would require ruling out every conceivable natural process. The standard of evidence is high, as it should be. Extraordinary claims require extraordinary evidence. Carl Sagan's dictum, often repeated, never outdated. The public reaction to GJ987c was excitement mixed with caution. Science media covered it as a mysterious discovery, not as evidence of aliens. The researchers themselves emphasized uncertainty and the need for more data. That's responsible communication. Contrast that with how some corners of the internet treat 3i Atlas. The trajectory anomaly gets framed as proof of extraterrestrial visitors, with little acknowledgement of measurement uncertainty or alternative explanations. The difference reflects the source. Professional scientists with institutional backing and peer review tend toward conservative language. Independent researchers publishing online, whether from genuine excitement or desire for attention, use bolder claims. Both stories, the exoplanet and 3i Atlas, belong to a rising class of what you might call data-driven whispers of the unknown. Our instruments are getting better. We're detecting finer details, subtler signals, stranger phenomena. Some of those phenomena will have mundane explanations. Some will reveal new natural processes, and maybe, just maybe, one will be the signal we've been searching for. The challenge is figuring out which is which before jumping to conclusions. What lessons does the exoplanet story provide for dealing with 3i Atlas? Patience, for one. The mystery molecule on GJ987c hasn't been explained yet, but no one is claiming aliens because we haven't explained it. Scientists are doing the work, building models, proposing new observations. The process takes time, transparency for another. The exoplanet data is public. Anyone with the skills can download the spectra and run their own analysis. That openness invites scrutiny and collaboration. If the 3i Atlas trajectory data were equally accessible, the controversy would resolve faster. Finally, the exoplanet story shows that unexpected discoveries happen regularly in astronomy. Nature is more creative than we imagine. Before attributing anomalies to intelligence exhaust natural creativity, still, the thrill of discovery remains. What if the next exoplanet atmosphere shows unambiguous biosignatures, oxygen and methane together, out of equilibrium plus phosphine and other gases life might produce? What if 3i Atlas's trajectory can't be explained, even with our best models and complete data? These questions hover at the edge of possibility. We're living in an era where detecting extraterrestrial life, or technology, is no longer science fiction. It's a legitimate possibility our instruments might reveal tomorrow or next year. The anticipation is part of the excitement, even as the skeptic in us reminds caution. Precision measurement is improving rapidly. Could we soon detect even more subtle anomalies in exoplanets or solar system objects? Let's explore how better tools change the game. Part 12. Advances in Astrometry Precision, GEA, Rubin Observatory Era. The Gaia Space Telescope, operated by the European Space Agency, has revolutionized astrometry. Launched in 2013, it has spent over a decade measuring the positions, distances and motions of stars with unprecedented precision. The third data release, Gaia DR3, published in 2022, contained data for nearly 2 billion stars, positions accurate to tens of micro-arc seconds, proper motions, how stars move across the sky over time, measured to similar precision, distance estimates from parallax measurements reaching thousands of light years. Why does this matter for objects like 3i Atlas? The star catalogue provides the reference frame for all astrometric measurements. When you image a comet or asteroid, you match stars in your image to Gaia stars and use that to calibrate your coordinate system. The better the star catalogue, the more accurate your target's position. Before Gaia, catalogues like Hipparcos or Tycho had positional accuracies around a milliarc second. Gaia improved that by factors of 100 or more for many stars. Errors that once plagued asteroid astrometry have been slashed. Gaia's proper motions matter too. Stars aren't stationary. They move through the galaxy, and that motion projects onto the sky as proper motion, typically milliarc seconds per year. If you use an old star catalogue without proper motions, or with inaccurate proper motions and you observe an asteroid years later, your reference frame is wrong. The stars have moved, but your catalogue doesn't know it. Gaia gives proper motions good enough that you can predict star positions decades into the future with high confidence. DR3 isn't the end, Gaia continues observing. Future data releases will refine measurements further and extend to fainter stars. Each release tightens the web of precision that astrometry depends on. For small bodies in the solar system, this means orbit determinations improve. Non-gravitational accelerations become easier to detect because the noise floor drops. Anomalies like the one claimed for 3I Atlas become easier to confirm or refute because systematic errors from bad star catalogues are minimized. The Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, is scheduled for first light in 2025 and will begin full survey operation shortly after. Rubin will image the entire visible sky every few nights, creating a movie of the universe. Every moving object, every transient event, every asteroid and comet gets tracked automatically. The survey will discover millions of new asteroids and comets. It will catch supernovae within hours of explosion. It will monitor variable stars and detect gravitational lensing events. For interstellar objects, Rubin is a game changer. Oumuamua was discovered after it had already passed perihelion, limiting how much we could study it. Borisov was found earlier, but still only months before perihelion. Rubin's cadence means the next interstellar visitor will likely be spotted while still far out, giving years of lead time. Trajectories can be refined continuously. Any deviations from predicted paths will show up in real time as residuals in the orbit fits. If an object maneuvers, Rubin will catch it. Rubin's astrometric precision won't match Gaia's for individual measurements, but volume compensates. Thousands of observations over months and years allow fitting extremely precise orbits. Non-gravitational accelerations down to 10 to the negative 10 AU per day squared could be detectable if the object is tracked long enough. That's the level where subtle effects like solar radiation pressure on small bodies or minute outgassing from distant comets show up. Early Rubin commissioning data has already demonstrated the system's capabilities, detected known asteroids and measured their positions to sub-arc-second accuracy. Discovered a few new near-Earth asteroids. Once the full survey begins, the data rate will be staggering. Terabytes per night. Processing pipelines will automatically detect moving objects, link observations into tracks, compute preliminary orbits, and flag anything unusual. Anomaly detection algorithms built into the pipeline will alert astronomers when something doesn't fit standard models. This brings us to the question, could anomalies like 3I Atlases be caught earlier with Rubin? Almost certainly. If an interstellar object starts deviating from its predicted path weeks or months before perihelion, continuous tracking will reveal the trend immediately. No waiting for amateur observers to notice. No ambiguity about whether the offset is real. The professional survey data, with robust calibration and error analysis, will settle the question. Either the trajectory is anomalous or it isn't. Implications extend beyond interstellar visitors. Near-Earth asteroids, objects that pass close to Earth and might someday pose an impact threat, need precise orbits for risk assessment. Tiny trajectory changes from the Yarkovsky effect, where absorbed sunlight re-radiated as heat creates thrust, matter for long-term predictions. Rubin will measure those effects routinely, improving our ability to predict asteroid trajectories decades into the future. If deflection missions like NASA's DART become necessary more frequently, precise astrometry guides them. Mapping the solar system's small bodies also tells us about its history, where objects come from, how their orbits evolved, what dynamical processes shaped the current architecture. The asteroid belt, Kuiper belt, Oort cloud all contain clues about the early solar system. Interstellar visitors like 3I Atlas offer glimpses of other star systems. If we catalogue their trajectories and compositions systematically, we start to understand the diversity of planetary systems across the galaxy. Artificial artifacts, if they exist, might reveal themselves through motion. A dormant probe in a distant orbit, inactive for millennia, might still betray itself by trajectory anomalies when we track it precisely enough. Rubin could discover such objects if they're out there. The odds are low, but non-zero. Every new survey finds surprises. Sometimes the surprise is a new class of natural object we didn't predict. Sometimes it's behavior we didn't expect, And maybe, someday, it's something that isn't natural at all. The future of astrometry is bright. Gaia, Rubin, and upcoming space missions like Euclid and Nancy Grace Roman will push precision to new limits. We'll measure the positions of billions of objects, track their motions over years, and detect accelerations at levels once thought impossible. This rising tide of data lifts all research. Questions that seemed unanswerable become tractable. Mysteries that lingered for decades get solved. And new mysteries emerge to replace them, because the universe never runs out of puzzles. In the context of 3i Atlas, the infrastructure now exists to definitively answer whether it's maneuvering. The tools, the telescopes, the star catalogues, the processing pipelines, all are ready. If the anomaly is real, confirmation will come. If it's artifact, that will be revealed too. The waiting period shortens as our capabilities grow. We might not have to wait years for an answer. Months could suffice. But motion anomalies aren't just about position. They could also be about propulsion technology, which brings us to recent advances in sail propulsion experiments and what they teach us about the feasibility of interstellar travel. Part 13, Plasma Sail, Solar Sail Experiments. In orbit. In June 2025, a CubeSat mission called HelioSail-1 deployed a 25 square meter solar sail in low Earth orbit. CubeSats are miniature satellites, often just 10 centimeters on a side, cheap to build and launch. HelioSail-1 carried a folded sail made of aluminized mylar, a few micrometers thick. After reaching orbit, the sail unfurled, spreading out like a metallic flower. Sunlight reflecting off the sail imparted momentum, creating thrust. The mission's goal was to demonstrate controlled attitude changes using only sail orientation, no thrusters. The results were mixed but promising. The sail deployed successfully. Telemetry showed the satellite's orbit changing as predicted by solar pressure models. But controlling orientation proved harder than expected. The satellite tumbled slightly, and the sail's attitude wobbled. Over weeks, engineers refined the control algorithms and achieved more stable pointing. The mission demonstrated that even a small sail could produce measurable velocity changes, several meters per second over months. Scale that up, use a larger sail and longer time, and you can achieve interstellar velocities. Solar sails work by reflecting photons. Light carries momentum. When a photon bounces off a reflective surface, it transfers twice its momentum to the surface, once on arrival, once on reflection. The force is tiny. Sunlight at Earth's distance provides about 9 micronewtons per square meter of sail. For a 1 square kilometer sail, that's 9 millinewtons. Sounds negligible, but in space there's no friction. That tiny force accelerates the sail continuously. Over years, the velocity builds. Given enough time and a light enough spacecraft, you can reach a significant fraction of the speed of light. Not human habitable speeds, but fast enough to cross interstellar space in centuries rather than millennia. The Planetary Society's LightSail 2 mission, launched in 2019, demonstrated sustained orbit raising using a solar sail. The sail was 32 square meters, and over weeks, it raised the orbit's apogee by several kilometers. That might not sound like much, but it proved the concept. Solar radiation pressure is usable for propulsion. No fuel required. As long as you're near a star, you have thrust. NASA's Near-Earth Asteroid Scout mission, unfortunately lost after launch in 2022, was meant to fly a solar sail to a near-Earth asteroid. The sail was 86 square meters. Had it succeeded, it would have demonstrated interplanetary travel using only sunlight. Lessons from that failure informed future missions. The engineering challenges are real. Deploying large, thin structures in space is hard. Keeping them oriented correctly is harder. But each mission improves the technology. Plasma sails are a related concept. Instead of reflecting photons, they interact with the solar wind. The stream of charged particles from the sun. A plasma sail generates a magnetic field that deflects solar wind particles, creating a larger effective area than the physical sail. The magnetic field acts like an invisible net catching the wind. Thrust depends on the strength of the field and the density of the solar wind. Plasma sails could be more efficient than photon sails in some regimes, especially farther from the sun where sunlight weakens but the solar wind remains. No plasma sail has flown yet, but laboratory experiments and theoretical models show promise. Generating the required magnetic field needs power, but not much if you use superconducting coils. A spacecraft could carry a small nuclear battery or radioisotope generator to power the coils, then ride the solar wind outward, combining solar and plasma sails. Using photons close to the Sun and plasma farther out might optimize performance. How does this relate to 3i Atlas? If the object is artificial, if it's using propulsion, sails are plausible candidates. A light sail accelerated by its home star could reach interstellar speeds, coast for thousands of years, then decelerate using our Sun's light as it approaches. The trajectory would look like what we see, inbound from interstellar space, decelerating as it nears the Sun, perhaps adjusting course using subtle changes in sail orientation. The thrust levels are low, consistent with the small accelerations needed to produce a 1,000,000-kilometre offset over months. What would we see? A large, thin sail reflects a lot of light. It should be bright for its mass. If 3i Atlas is dimmer than expected, maybe the sail is edge-on to us, minimizing the visible area, or maybe it's been retracted or damaged during the long interstellar journey. Micrometeoroid impacts over millennia could erode the sail, reducing its effectiveness. Or maybe there's no sail at all, and the propulsion is something else entirely. Compare the thrust-to-mass ratio. Helios Sail 1 achieved about 10 to the negative 7 meters per second squared. For a larger sail, or one closer to the Sun, you could get higher. To shift 3i Atlas's orbit by 1,000,000 kilometers, you'd need accelerations around 10 to the negative 6 to 10 to the negative 5 meters per second, squared sustained over months. That's 1,000 to 10,000 times higher than Heliosail's performance. Not impossible, but you'd need a very large sail or very low mass. If the object is mostly hollow, a scaffold with sail material stretched across it, the mass could be low. But that's speculation built on speculation. Could we detect a sail? High-resolution imaging might reveal extended structure. Polarimetry might show the characteristic signature of light reflecting off a thin film. If the sail is actively adjusting its orientation, we might see periodic brightness variations as different parts catch the sunlight. None of that has been reported, but perhaps no one has looked carefully enough yet. The broader point is that sail propulsion is no longer science fiction. We've built sails, we've flown them in space. The technology is primitive compared to what an interstellar mission would require, but the physics is proven. If another civilization developed sails 1,000 years before we did, they could have sent probes across the galaxy. Those probes might be passing through our solar system right now, and we'd only notice if we looked at their trajectories carefully enough. Thrusters in space are real. We built them. The question is whether anyone else did too, and whether one of their creations is currently rounding the Sun's 70 million kilometers from Earth. If propulsion is possible, detecting it requires watching for the signs. Which brings us to how artificial intelligence might help us spot anomalies we'd otherwise miss. Part 14. AI-powered anomaly detection in telescope data. In March 2025, an AI-driven project called Cosmic Outlier Search announced it had flagged 37 objects in archived sky survey data that didn't fit any known classification. The team trained a neural network on millions of images from the Zwicky Transient Facility, a survey telescope in California that scans the sky nightly for transient events. The neural network learned what normal stars, galaxies, supernovae, and asteroids look like. Then it scanned through data looking for anything that didn't match the learned patterns. Outliers. Most of the flagged objects turned out to be instrumental artifacts or misclassified known objects. But a few are genuinely interesting. One was a faint, fast-moving object that turned out to be a distant Kuiper belt object on an unusual orbit. Another was a variable star of a type rarely seen, possibly in a phase of evolution that models didn't predict well. The project demonstrated that machine learning could sift through vast datasets and find needles in haystacks, things human researchers would never notice because there's too much data to inspect manually. Anomaly detection algorithms work by learning the statistics of normal data, then flagging anything that deviates significantly. Techniques include clustering, where you group similar objects together and look for singletons that don't belong to any cluster. Autoencoders, neural networks trained to compress data and then reconstruct it. Flag objects that can't be reconstructed well because they're unlike the training set. Isolation forests and one-class SVMs are other statistical methods. The key is defining normal broadly enough to capture real diversity, but narrowly enough that genuinely strange things stand out. For time series data, like the brightness of an object measured over multiple nights. Recurrent neural networks or transformers can learn typical patterns and flag unusual ones. A star that brightens steadily over weeks might be a supernova. One that flickers irregularly might be an eclipsing binary or a variable star. One that shows a pattern unlike any known class might be something new. Applied to astrometry, AI could detect motion anomalies automatically, train a network on the trajectories of thousands of asteroids and comets, teach it what normal orbits look like, including the expected range of non-gravitational accelerations, then feed it the observations of 3i Atlas. If the trajectory deviates significantly from the learned distribution, the algorithm flags it. This doesn't prove the anomaly is real, but it prioritizes it for human follow-up. One concrete example is the Asteroid Terrestrial Impact Last Alert System, ATLAS, a survey designed to find near-Earth asteroids. ATLAS uses machine learning to distinguish real moving objects from artifacts like cosmic rays or satellite trails. The algorithms have been refined over years and now catch over 99% of real objects while rejecting most false positives. Similar techniques could be applied to interstellar object tracking. The challenge with AI is interpretability. Neural networks are black boxes. They give you an answer, this object is anomalous, but they don't always explain why in terms humans understand. A flagged object might be anomalous because of a subtle pattern in the data that makes perfect sense once you see it, or because the network learned some spurious correlation during training. Validating AI findings requires human expertise. The AI narrows the search space, but humans decide whether the anomaly is real. If 3i Atlas's trajectory anomaly were input to an AI-trained system, what would happen? If the offset is real and represents a sustained deviation from gravitational plus standard, non-gravitational models, the system should flag it immediately. The trajectory would lie outside the distribution of a normal cometary orbits in a statistically significant way. On the other hand, if the anomaly is caused by measurement errors that look random to humans, but have subtle correlations, the AI might either miss it or flag it for the wrong reasons. AI systems are only as good as their training data and their ability to generalize. Ethical and epistemological questions arise. If an AI flags an object that hints at engineered behavior, who verifies it? How do you balance excitement at a potential discovery against the risk of false positives? AI-driven searches will produce many false alarms. Most anomalies will have mundane explanations, but occasionally one won't. The challenge is not getting desensitized to alerts, not dismissing the 99th false positive, and missing the one true discovery. Citizen science platforms are starting to incorporate AI. Projects like Galaxy Zoo, where volunteers classify galaxies, now use AI to pre-screen images and send only the hard cases to humans. This hybrid approach leverages AI's speed and human judgment. For astrometry, a similar system could work. AI scans all observations, flags potential anomalies, and humans with telescopes follow up. The feedback loop improves both the AI, which learns from human corrections, and the science, which benefits from AI's tireless scanning. Could AI have detected 3i Atlas's drift earlier? If the observations were fed into an anomaly detection pipeline in real time, possibly. But that requires infrastructure. Someone has to build the pipeline, train the models, and maintain the system. For newly discovered objects, there's often a lag between discovery and systematic monitoring. By the time enough data exists to train a model, the interesting behavior might already be over. Prospective anomaly detection, where you watch objects from the start and flag deviations immediately, is the goal. Rubin Observatory's alert system will move toward that. AI might also help separate natural from engineered signals. And suppose you train a network on the light curves and spectra of thousands of comets. It learns the patterns of natural outgassing, dust emission, fragmentation, then you show it 3i Atlas's data. If the data doesn't match any natural pattern the network has seen, that's a clue. Not proof, because maybe it's just an unusual comet, but a clue. You'd then train another network on hypothetical engineered signals, propulsion exhaust signatures, structured plasma distributions. If that network matches the data better, you've narrowed the possibilities. The future of astronomy is humans and AI working together. AI handles the scale, the millions of objects and billions of data points. Humans handle the interpretation, the skepticism, the creativity to imagine what might be happening. This partnership is already transforming the field. Discoveries that would have taken decades now happen in months. Anomalies that would have been buried in noise now get surfaced and studied. Whether 3i Atlas is one of those anomalies that survives scrutiny or gets explained away, the tools to answer that question are better than ever before. The question is what we do if motion anomalies become a new frontier, which brings us to policy and philosophy. Part 15, Policy and Philosophical Ramifications, Interstellar Object Governance. Imagine the confirmation comes. Multiple independent observatories using rigorous methods verify that 3i Atlas is maneuvering beyond any natural explanation. Spectroscopy reveals anomalies consistent with technological processes. Imaging shows structures that don't look natural. The scientific consensus shifts from skepticism to acceptance. This is an artificial object under intelligent control from outside the solar system. What happens next? First question: who owns this information? If the confirmation comes from a government-funded observatory, does that government control the announcement? Do they classify it for national security reasons or release it openly? The tension between transparency and control is immediate. In the best case, the discovery is announced through normal scientific channels. A paper is submitted to a journal, press conferences are held, data is shared. The global scientific community and the public learn simultaneously. In worst cases, information leaks through unofficial channels before official confirmation, creating confusion. Or governments sit on the data while deciding how to respond and rumours spread. International coordination becomes essential. No single nation owns space or has jurisdiction over interstellar visitors. The United Nations Office for Outer Space Affairs coordinates space activities under treaties like the Outer Space Treaty of 1967. That treaty addresses the rights and responsibilities of nations in space, but was written with human activities in mind. It doesn't cover what to do if you discover an alien probe. New frameworks would need to be invented on the fly. SETI, the Search for Extraterrestrial Intelligence, has post-detection protocols. If a credible signal from extraterrestrial intelligence is detected, researchers are supposed to verify it, inform relevant authorities, and then make a public announcement. The International Academy of Astronautics has a SETI permanent committee that maintains these protocols. But those protocols assume radio signals, not physical objects. Would the same principles apply? Probably. Verify thoroughly. Inform globally, avoid unilateral actions that might affect all of humanity. Ethical frameworks guide how we approach such discoveries. The precautionary principle says when facing potentially significant consequences, especially irreversible ones, err on the side of caution. If there's any chance 3i Atlas poses a risk, understand that risk before taking actions that might provoke a response. On the other hand, the principle of transparency says the public has a right to know about discoveries that affect humanity collectively. Balancing these principles is tricky. Too much caution leads to secrecy and conspiracy theories. Too much openness leads to panic or misinformation. Risk assessment is complicated when the object is under intelligent control. Natural asteroids follow predictable paths. We can calculate impact probabilities and plan deflection missions if needed. An object that can maneuver changes that calculus entirely. Where is it going? Is Earth a destination or just a waypoint? Does it pose any threat or is it simply observing? Without communication we can't know its intentions, assuming the worst risks overreaction, assuming the best risks complacency. Middle paths involve monitoring continuously, preparing contingency plans, and attempting communication. Attempting communication raises more questions. Should we signal the object? If so, what do we tell it?